Well, if you're tuning in right now, please share where you're joining. Albert is joining somewhere near Disneyland. I'm actually based in Seattle, close to like the Amazon spheres and stuff. But yeah, I think we can go ahead and get started. So if you're also joining, let us know about your Hudi or StarRocks MinIO experience. We would love to see where you're at in your like data journey or data infrastructure journey. But I'm Nadine. I'm Apache Hudi contributor. I'm with One House. And Albert, do you want to go ahead and give a quick intro?
Sure. So my name is Albert. I'm one of the DevRel people at Stellar Data. We're the primary sponsor of the StarRocks Linux Foundation project. So I used to work at MongoDB, Red Hat before IBM bought them, and then also IBM.
Oh, awesome. Okay. So let's go ahead and go over like a quick agenda. I'm actually going to go do like a quick Hudi overview, but I'm actually going to talk about some concepts around Hudi that's related to the demo. So it won't be like a complete deep dive into table services and stuff because that's not going to go over part of the demo today, but we'll go over some concepts. And if you have more questions, you can write them in the chat, and I'll be scanning the chat and hopefully be able to answer them as well. And then I'm actually going to pass it to Albert to do like the StarRocks overview and the Hudi StarRocks integration. And then Albert will take it and talk about the really cool demo that he built. So let's go ahead and do a quick deep dive into Hudi table types and query types. So Hudi stands for Hadoop's upstarts, deletes, and incremental, and it spans its capabilities beyond, just a typical data lake. And with the Lakehouse, it incorporates features from a data warehouse with like ACID compliance and things like that, but also concepts from a data lake where you can store a lot of data. So with Hudi, we've actually transformed a data lake into this like data lakehouse with the data warehouse capabilities. And you can almost think about it. I like to really use this analogy a lot. But if you remember way back when there was like Pokemon characters and you have this baby Pokemon, that's kind of akin to like a data lake with just like throwing data, raw data there. There's no structure, there's no indexing, there's nothing. It's an immutable store. But then, you have this metamorphosis with these characters and they become bigger and stronger. This is what this lake house is. It's like another generation of the data lake where you can not only ingest data and process data, but there's these features and services equipped with the data lake with indexing or clustering and compaction and things like that. So it makes being able to use that data at like terabytes, petabytes, exabytes scale so efficiently that you would otherwise have if you just threw it into a raw data lake. So Apache Hudi is a comprehensive platform designed for data ingestion and processing. And like I mentioned before, it's actually equipped with features and services that maximize both reading and writing data. So if you look at the diagram at the foundational level of this platform is your data lake storage. You can have S3. In this case, in the demo, we're actually going to be going over, the lake storage is actually MinIO. And then this is where basically all your data resides in some format like Parquet. Now, on top of this, you have your open file data format. And then on top of that, you have your transactional layer. And this is where Hudi's true power shines, because it offers multiple services like the indexing services, or you have concurrency control, you have table services and things like that to help manage your data, so it's easier to use and easier to query as well. And these services collectively offer significant enhancements to your data and table management. And in this case, we're going to talk about different table types that Hudi offers, and we're also going to go over the different query types as well. We won't go over into all of these deep dives here, but if you're interested in learning more, you can check out our Hudi LinkedIn, which has a lot of LinkedIn live sessions. I go over different things, and I can share some inside the chat in a minute. So after your data has been successfully ingested and managed, then Hudi offers the ability to connect and process the data with popular computation engines like StarRocks. Hence why Albert from StarRocks is joining us. But we also offer other popular integrations as well, and I can share the docs to that and the chat once we're kind of done. So I kind of want to go over really quickly why you would want to choose Apache Hudi for your data storing and processing, and kind of like the differential features of what makes Hudi really, really special. And there's a few of them. One is fast upserts and deletes. So Hudi supports data mutability and offers multiple indexing capabilities and mechanisms. So if you're working with streaming data like Kafka, Flink, Spark structured streaming, and you need to have mutability, obviously, because you're going to have duplicates and things like that. Hudi is a really great choice, and Hudi was built from the very beginning to support these write operations. The next thing is incremental processing. So if you're not familiar with incremental processing, basically whenever, we'll go over it when we talk about table and query types, but basically when you get new data, you want to be able to just update the rows with that data and avoid the full table scans and table rewrites. And incremental processing does that. It helps you avoid that. So when it comes to computation, like how you manage your compute resources, incremental processing reduces the compute resources that you might need. And the other thing that's really cool with Hudi, it's been proving time and time and again that it works at scale. ByteDance is using a single table exabyte scale, Uber, and so much more. The other really cool feature is the interoperability of the query engines. And in this case, we're going to be talking about StarRocks. And then depending on how you define your configs, it's really easy to manage and kind of automate some of your table services. So automatic file sizing, cleaning, clustering, and more. So these are just like few key points of what makes Hudi really, really special. And so I kind of want to go over the table types now and kind of just do a little bit of the query things and or the queries available to these different table types, and then I'll pass it to Albert. So one of the table types that Hudi offers is a copy on write table, and it basically contains base and columnar file, and each commit produces a new version of this base file. And so as data gets written, updates to existing file groups produce a new file size for that file group. And then within that, there's a commit time that's associated with that. So in other words, with copy on write table, you implicitly compact these files on every commit during the write during your data ingestion, and this means that the write amplification for a copy on write table is a little higher, but the read amplification is basically zero because you can just read the Parquet files and then get the results. So with a copy on write table, let's say you have your first ingestion at commit time 0, which is the blue boxes, and you want to be able to run a snapshot query. A snapshot query returns the full table state at that point in time. So if you look at the blue boxes, if you have A, B, C, D, E, and you want to run a snapshot query, it will just return the full state. And if you go to commit time 1 with like the yellow box, it will actually return the full states. If you want to run a snapshot query, you can see between the updates between commit time 0 and commit time 1, A gets updated and D gets updated. So in this case, if you run a snapshot query on the yellow boxes, you'll return the full state. So you'll get the update from A, B, C, D, which is the update, and then E. Now, as I mentioned earlier, one of the ways Hudi truly shines is with incremental processing. So in Hudi, you can actually run an incremental query. Now, what is that? It just actually, incremental query just returns the changes that have happened. You can use that changes and then update your downstream tables with those changes. So if you run an incremental query on commit time 0, everything is just newly ingested, so you're going to return everything. But if you go to the yellow box and you want to run an incremental query, it will just return those updates, in this case, the A and D, which have been updated, so A prime, D prime, and so on and so forth. Now, the next table I kind of want to talk about is the merge on read table. So a merge on read table is a superset of a copy on write table in the sense that it supports read op, in the sense that it also supports a read optimized query where you just read all the basic columnar files based on since the files have been last compacted. Additionally, when you get new updates and stuff, it actually writes those updates to what we call log files. And then at compaction time, what happens is you can merge all these little log files to new base files, and you form a new version of this base file. So let's take a look with the merge on read table and the different query types. So one of the things I want to highlight is because you're writing directly to these log files, the write amplification is actually 0 because you're just quickly writing, but the read amplification is higher because depending on, you'll have to read all the log files or all the base files, and that's a little bit more expensive to do. So if we go through the snapshot query, similar to the copy on write table, it will return the full state of what the table is. In this case, the snapshot query, if you run it, let's say on commit time 1, it'll return the updates that have happened in the log files in addition to non-changing data. So in this case, if you were to update A and D, the snapshot query will return the updates within A and D and then the non-changing data as well. Now, if you run an incremental query similar to copy on write, it will just return those updates. In this case, A and D will be returned if you're looking at commit time 1. Now, if you run and read optimize query, it will just return the latest full base files, which are the Parquet files. In this case, it'll be A, B, C, D, E. So it's not returning any updates or anything like that. But if you look at commit time 3 and you run a compaction, you now have new versions of the base file. So if you run and read optimize query, it will return all the updates that have happened at the base file with the new version of the base file. In this case, you'll return the updates that have happened with A, B, C, D, E, or F, and new inserts as well. So read optimize query returns the data from since the files have last been compacted. There are different trade-offs between choosing copy on write and merge on read table. But in general, if you can afford the data latency and you're running batch workloads, copy on write is really good for this. As we mentioned, the write amplification is a little higher, but usually you can afford that. But if you're working with streaming data, you need to have fast writes and things like that. The merge on read is really, really good. And we already went over like the write and read amplifications and stuff. But depending on your workloads and kind of the SLAs you have, one of these will be really good. So these are the different query types, and this is just kind of summarizing the different queries. I won't go into too much detail since we just went into detail about it, but you can also, I didn't go talk about time travel query, but you can also run a time travel query between certain times depending on the range of times that you specify. So Hudi is proven at massive scale, and the community is constantly growing. We actually just crossed 4,000 members on Slack. We're continuing to grow on all different types of platforms. And whenever, we're pre-installed in a couple of cloud providers, we have a lot of AWS users, Google Cloud, Alibaba Cloud, and so on. We have tons of PMC members, contributors, committers, and then we have a Reach ecosystem as well. So if you're interested in joining the Hudi community, you can join on Slack. You can follow us on LinkedIn, on Twitter, and also YouTube. We're going to be doing so many live events and a lot of enablement on that end. So now I'll pass it. Actually, we'll stop my screen share, and I'll pass it to Albert for the StarRocks overview and the demo.
All right, great. Thank you, Nadine. All right. So what is StarRocks? So I'm gonna expand the picture a little bit here. So what is StarRocks? So StarRocks is a Linux Foundation project. Just to give you an idea about it, is that we are a next generation real-time OLAP database. So what does that mean? So OLAP database, obviously we're using it for analytical workloads. What do we mean by real time? That means that we actually can do sub-second response times on petabytes of data or more. And that next generation, I'll talk a little bit more about what that means and what are some of the characteristics of having a next generation system itself. So being a Linux Foundation project is great. We get a lot of visibility from that. We're also a CNCF member itself. And the thing is that it allows us to go and access all the nice resources around globally for our project, right? So we are 7,500 plus GitHub stars, more than 350 contributors from all around the world. We have over 18,000 community members, and we have a wide range of different users of our system, right? A lot of people, and the analogous that a lot of people make us a comparison to is that we're an open source replacement for Snowflake, for BigQuery, for Redshift, for all intents and purposes, right? In the upcoming demo that I'll show you a little bit later on today, we're actually going to use StarRocks more as a query engine on top of Hudi, as opposed to maybe some of the other models we have, which is StarRocks with its own attached storage within the product itself. So as you can imagine, Bing is, comparison to other OLAP vendors, right? What do we do from that standpoint? We're pretty much almost exactly all the other things that you would expect from an OLAP system, right? So we have a web UI for the business analysts and for developers to go use. We also have another UI that's for administrators to manage and deploy and monitor their existing environment, right? The core of the product itself is the query engine itself, which is the StarRocks Vectorized engine, right? It's something that we built in-house from that standpoint. And then underneath that is that if you do pick the mode that has attached storage, we just write that in normal in the StarRocks table format. Or alternatively, you can swap out that storage and connect to something like Apache Hudi on S3, right? Some of the other things that is also interesting from that standpoint, and I'll talk about this a little bit more, we're cloud native with a Kubernetes operator, and we have this idea of separation of compute and storage. So what is that exactly, right? So this is what we mean by StarRocks with an open data lake, right? So there's a lot of vendors who basically say, hey, you know what, we have proprietary compute, proprietary table format, proprietary storage, right? And there's some vendors that have like a hybrid of those approaches. We're just open source across all those things. So open source compute, we use open table formats to store our data. And then for storage, we're using S3. So in this case, you kind of see the architecture. We have the StarRocks OLAP cluster, right? And we're using the shared data architecture. Shared data to us means separation of compute and storage. We also have a different architecture called shared nothing. The shared data is how Snowflake and BigQuery is actually deployed, right? So there's an elastic compute layer, which we call the front end nodes. That provides is our emulated MySQL wire compatible protocol. And then you have storage nodes that basically executes the query plans and then persists that data into long-term storage, right? So we essentially only have two tiers, front end tiers and CN nodes from that, or back end nodes from that standpoint. You'll also notice that we point to a local S3 bucket. So think of that local S3 bucket as like RBAC, usernames, passwords, all the kind of things that you expect from a data warehouse from that standpoint, right? And so in this situation, we're not using that local S3 bucket for all of our databases and for our tables. Actually, what we do is we connect to a Apache Hive Metastore, and behind the scenes of the Hive Metastore is backed by Apache Hudi with the S3 bucket. Right. And so if you're not familiar with this type of architecture, this is also very analogous to kind of say, Snowflake with managed tables, right? So you got your own Snowflake environment, and then you can connect to something that's remote. And we're actually storing everything inside of Apache Hudi. Okay. Talk a little bit about our product itself. So we're on the 3 series. We just released 3.2, and we're a couple months away from our 3.3 release. So what are we spending our time in, right? So first of all is we're building more and more core data warehousey features, right? So like I mentioned, we're a data warehouse on top of a data lake. That's why it's called Data Lakehouse, right? It's like this building that you're on top of this lake infrastructure. And a lot of things what you don't get from a data lake. So Nadine alluded to this, so things like materialized views, things like security, things like being able to do is query caching or having a query layer itself, right? Like supporting the SQL protocol and stuff like that, right? So what you want to be able to go do is you want all the goodness of the data warehouse features, but instead of expensive local storage, you're actually storing all that data on cheap S3 storage, right? And I'm not sure if you knew the cost differences, but for instance, $1 of EBS, S3 storage for that same gigabyte is 5 to 10 cents. So you can imagine if you have terabytes or petabytes or even zettabytes of data, it's very, very expensive to store everything on local disk. It's much, much more cheaper for you to store all that data in S3. And a lot of data warehouses cannot do that. They have to store everything on a local disk, right? So you have this thing which you have to elastically pay more for the compute side and for the storage costs, right? And there's a lot of little gaps here and there. But anyways, long story short, data warehouse features is what we're working on to expand more and more of that capability. The second thing that we're working on is that I mentioned here in the previous slide, we actually have two different architectures, which is the shared data, which is how BigQuery and Snowflake is deployed. And the share nothing model is how Redshift is actually deployed. If you're familiar with Redshift, you know, there's compute and storage on the same node. If you want to elastically scale, you have to scale both of those together as one unit, right? The downside with that is that you have to shuffle data between nodes. So there's some expensive costs from that, as opposed to the shared data model. All the nodes are pointing to the same S3 bucket, so there is no data shuffling from that standpoint. So we had in the 1 and 2 series of our product, it was a shared nothing model. In the 3 series, we released shared data, and right now we're working on making parity in terms of feature sets between the two architectures, so that no matter if you pick shared nothing or shared data, you will get similar features. The other thing that we're working on is supporting all the popular table formats, right? So this is us being able to say that we want to be one of the fastest query engines for Apache Hudi. And feel free to benchmark us. We're pretty confident about our ability to query Apache Hudi data. Take us for a spin from that standpoint and benchmark us against any other OLAP system in the market. Okay, so what are some of the major features of the StarRocks itself, right? So what makes us really different than all the other OLAP systems in the marketplace, right? So one is our vectorized query engine with SIMD, right? So vectorized, for all intents and purposes, right, means that you store the data in columns from that standpoint, right? Why in columns, right? Well, most of the time for an OLAP database, you're actually doing aggregations. So you're talking about summations, or you're talking about some type of, like, the summation would be, give me all the sales for the end of the week, right? Tell me how many employees are in this region, right? You know, things of that nature, where you're applying an operation to the same set of data, but it's a lot of that data, right? That's one piece, right? The other, and there are other, you know, databases out there that are vectorized from that standpoint, which I would say majority of the market right now, probably more than 50%, has moved to vectorized, when in the past this wasn't the case, right? But what is unique is this SIMD. So SIMD stands for single instruction multiple data. So a lot of the databases out in the current market is that for one, say for instance, CPU cycle, you can do one operation, either a read or a write. An SIMD, single instruction, multiple data, it implies that for a single instruction, I will work on multiple pieces of data at the same time, right? Now think about that. This technology doesn't really work well for OLTP, like MySQL and Postgres, because you're usually only manipulating one row from that standpoint, right? But when you're doing an operation like summation, you're actually applying the same operation across multiple pieces of data, a range of data from that standpoint. And this is where that SIMD was really, really, you know, great for us to go use, right? And although this feature has been in Intel chips for a while from that standpoint, it was only theoretically used in written in academic papers about 10 years ago. And the newer generation of OLAP systems, in fact, inside of the OLAP world, I only know of 3 databases that uses SIMD. Obviously, we're one of them from that standpoint. And this is why we dominate, is the performance charts from that standpoint. Also, as a little tip, so what was SIMD really originally built for? It was actually built originally for gaming and for music. So the idea here is that if you had a game with light rays instead of you doing a for loop and individually moving each particle of light in the game, is that you can apply is an operation to move all that light as an entire series, right? And so you can imagine doing the same thing instead of us manipulating every single individual row or column from that standpoint, or every single entry. We apply an operation across everything, and that allows us to be 3 or 5 times faster than other non-SIM databases. The other thing about StarRocks is that we advocate for is that we have this idea of, say, for instance, pipeline free. And what we mean by pipeline free is that traditionally for most databases, you have third normal form in some OLTP like MySQL or Postgres, and then you write some pipeline scripts to denormalize it to wide flat tables. So you might have 15 tables in MySQL, and then now you have one table with like 50 columns in there, right? And it's kind of it's a lot of work to keep those things in sync all the time. And we're like going, what if we can give you the same performance or near same performance of a wide flat table, but you can do joins, right? Wouldn't that make your life easier? So then if you had 15 tables, you just need to just move the entire table over, and that's it. You don't have to do any denormalization. You don't have to manipulate this in any way from that standpoint. Theoretically, you could just move the table on over, just copy the table on over to the OLAP and just do ad hoc joins whenever you see fit, right? So one of our biggest things out in the marketplace is that we have the most join algorithms of any single open source database that's on that. And that's why when you do joins within StarRocks, you'll see that we're much faster than other places, other open source projects from that standpoint. In fact, one of these ones I talk about here is Shuffle Join. There's another open source project that has an open PR for 2 years on it, and they said it was too difficult to go and do it, and so therefore they just didn't bother to go do it at all. And as you can imagine, shuffling data between nodes is really, really an expensive operation. And if you can do it efficiently, this is how you can get a lot of performance when you're doing billions to joins to billions to joins to millions of joins, right? Another thing that we specialize in is our SQL Optimizer. So if you're not familiar about how databases work, is that think about it when you execute is a SQL query. We, on the back end, we enumerate all the various possibilities of how that SQL can run. And we generate statistics against all those plans, right? In fact, you can run some commands to see all the potential possibilities of how we can execute the SQL. And what we do is that with the enumeration of all the various plans, and we have the statistics for it, we pick the one that is the fastest as how we execute those things. So when you think about things like, you're like, maybe as a developer, you're kind of like, oh, if I reorder the SQL in a certain way, you kind of get somewhat performance, right? Think about it as that we do it behind the scenes from that standpoint. So you don't really need to go and, build the most optimal SQL command. We'll actually tear it apart and try to figure out what's the best way to execute it the fastest single way, and then rewrite it to be built in our system. So we actually use a hybrid base. We are rule based in some areas. We are cost based in others. And ultimately, from that standpoint, that's why we get fast execution of whatever queries you kind of throw against us, right? Another thing in a database is that you don't get typically in, say, for instance, the open table format is a cache system, right? And so as you can imagine, when you're executing a SQL query here, there are many things that you can potentially cache, right? You can cache the intermediate results of a join. You can cache is fragments of pieces of data. You can also cache the raw data itself, right? So all these things, right, lead to performance enhancements from that standpoint. Almost every single open source OLAP system has a cache, right? There are some open source projects out there where the cache isn't as great, or they sell you is a a enterprise version of cache from that standpoint that runs a little bit better, or even they have is a closed source version of cache that they don't actually even open source into the marketplace, right? So we don't gatekeep from that standpoint. Our cache that we have within our product and with that and our enterprise version also is the same one from that standpoint. And with better cache systems, obviously, you know that we can go and accelerate query efficiency. So in certain cases, depending on how it is, we could get 3 to 10x to even more in terms of performance enhancements, right? And this matters also for another thing too. So you think about things where you have EBS volumes or even on data on S3 buckets, right? So the thing is that, you don't want to, first of all, you have the network latency, and we can't fix that part. But as much of what we can do for caching the data, the raw data in the S3 buckets, that allows us to go and basically make queries faster and faster and faster. I also mentioned a little bit more about this compute and storage, which we call the shared data architecture, right? So why people care about this, right? So the thing is that we've always thought about in database design is like, wow, we have to have this expensive database like infrastructure in order for us to query all this data, right? What if we can be much, much more thrifty with our computing resources? So that's the idea of compute and storage, separated compute and storage. So for instance, if I need more compute capacity, I just expand that tier of containers, right? Or that tier of nodes. If I need more storage, then I just expand those tiers from that standpoint. So in certain cases where you're saying like, hey, maybe I have a customer-facing, user-facing applications. For instance, StarRocks was originally built as an ad bidding engine. So you can imagine that you need current prices and historical data, and people are just querying all these different keywords, right? Thousands of people are querying all these different keywords to see what are the prices. You might say, for instance, I need 100 front-end nodes, but I don't need that many storage nodes. Maybe I only need like 10 or 20 from that standpoint, right? Or you might be in a different situation that you say, hey, you know what? We have a lot of data, but we don't really need all this excess query capacity because why? We have a lot of historical data, but it's only not used that often, right? So you could have like, say, for instance, 3 nodes of front end and then 10 nodes of storage on the back end, right? So we provide you this. We also, in our Kubernetes operator, which you can deploy in your own data center, it also has horizontal scaling built on in. So then you can go and scale these tiers independently. All right. The last thing we're going to talk about, which I really like, is that, as you know, there are hundreds of databases that are out there. You go to DB engines and you can see a whole list from that standpoint. And everybody comes out with a database with their own dialect, right? So at StarRocks, we didn't go and build another dialect. So basically what we did was we built a MySQL emulated layer. So essentially, in order for you to talk to StarRocks, all you have to do is a MySQL client. You write MySQL SQL commands. You execute MySQL commands to. So because we are a MySQL wire compatible protocol, any app that understands MySQL, so like things like Superset that has a MySQL driver from that standpoint, you just use the MySQL driver and you can automatically go and push in and get data out of StarRocks. All right. The other bonus too is that we also have, we do support one dialect, which is Trino. So if you have Trino and you didn't want to migrate all those Trino SQL into a MySQL statement, you can just set the system to say understand Trino, and boom, you can just copy paste your commands on it. So you can find us on our community website at starrocks.io, and then we also have an enterprise version. So that has a lot of the security features and some other additional benefits. That's at stellardata.com. And we also provide a cloud managed service off of cloud.stellardata.com. So let's get to the demo from that standpoint, right? So So just imagine that you are a big e-commerce company and you're on the web analytics team. So you're on the merchandising team, and in real time, the website actually writes in is web logs into Amazon S3. So they're just streaming data in all the time from that standpoint into to Amazon bucket. In Apache Hudi format. And so what we go do is that StarRocks can just plug in to that S3 bucket on Hudi, right? And be able to do some data analysis from that point of view. And so we're going to go and be that data analysis person. All right. So I'm going to bounce out really quick here. So so what we did is that we actually have is a website here. It's off of GitHub, and it has a set of instructions, and I'm just going to go through pieces of it. But what we do is that in this example, we provide you is a Docker Compose file, and a Docker Compose file is going to go and deploy its several assets in here. So we have the MinIO, which is going to be the S3 bucket. We also have is the Apache Hive Metastore. So that's going to be backed up by Postgres itself. So this is the Hive Metastore with the Postgres backend. We also have StarRocks, the front end and the back end nodes. And we're going to have as an Apache Spark job, basically emulating the traffic coming on in from the website, writing into the S3 bucket itself, right? So the first thing that you go do is you set up your Docker environment and make sure you provision enough memory from that standpoint. So I actually provision a whole bunch. You just need at least 16 gigabytes. I actually allocate more because I've got other demos and whatnot, right? And then you go log into MinIO. So in MinIO, you're going to create several buckets. So I created one bucket here, which is going to have some of the raw data. Here I have some user behavior data, and I also have some item data. And then you're also going to have another bucket here called Hudi test. So Hudi test is where you're going to actually store all the Hudi files in itself, right? Next thing that you're going to go do is that we're going to go and run is the Spark job in order for you to go and load the data. So if I go back to Docker desktop here, all right, you can go log into the Spark. You just go click at it, push exec. You know, you can type in bash. It'll show you the command line. I can go into bin, right? This is a Spark 3.2 environment. It actually has an older Hudi file, but I'm going to set it some commands here to upgrade the version. And you'll see here, I'm only going to use some 16 gigabytes of RAM. So I can go and execute this. Right, and this then launches the Spark shell that's going to go and be able to execute as Scala. And so here I have basically two Scala, Scala scripts from that standpoint. One is to load is the user behavior Parquet file, right? So this is going to be 87 million web events, and it's about 1.1 compressed of data. And then there is another one here, which is the item table. This is going to be, I think, 9 million some different types of items. And so the reason why we're going to have two is that we're going to do a join between these two tables themselves, right? So, what you would do is that I have a script here. You basically copy is the data. It's copy the script itself, and then you go and paste it into the environment, right? So once you paste it into the environment, it's gonna go and execute this. And depending on how much data it is, it may take, like for this one, I think it's about 30 seconds. But in some other situations, it'll be, 3 minutes or 4 minutes. I think it's the 1.1 gig is a little bit longer from that standpoint. So this is going to run, and it's basically going to not just write the Hudi data in the various S3 buckets, but you'll notice that I'm using bulk insert, and I'm also synchronizing the data into the Hive meta store that I have locally, right? All right, so what's that? So after that, right, now we've completed the process of emulating is a streaming load from the website into an S3 bucket, and it's just constantly writing data, right? Just imagine it's constantly writing data. And so the next thing here is that I'm the business analyst, right? So now I'm wearing my business analyst hats. So I want to go and query some of this data. So I'll just use my MySQL client, right? Connect to MySQL using the MySQL connect to StarRocks, right? And essentially, I run is only one command. And this one command tells StarRocks to say, hey, don't look at my local disk. Look at this other place, which is Hudi on S3, right? It's being stored on MinIO, right? Give it some username and passwords, and also look into this HMS system for the metadata itself. And then I'm going to run some commands here that's going to set is my queries to be executed. So I'm just going to execute this. And you'll notice now it says, hey, okay, I did a count on user behavior. I did a count on item. And that if you look at the numbers here, it's about, 87 million. Sorry. And it's 4 million items, not 8 million items. I keep on getting that stuck in my head. So it's 4 million items from that standpoint. So that I have all these data entries on in. So great. I can see the data itself. So as a merchandiser, the first thing I'm going to ask is that I want to understand the e-commerce purchasing funnel, the conversion funnel, right? And so I have this wicked SQL SQL command that basically is going to look at all the 87 million web traffic events, right? Inside of the data, it's actually going to show whether or not a user X is on the product view page, or are they on the shopping cart page, or are they on the buy page, right? There's also some other pages, but those are the big three categories I want you to focus on. And I'm going to bucket some of the I'm going to bucket the data in certain 30 minute intervals of a specific timestamp, right? So the idea here is that I want to go and understand is how many people look at the detailed product page, how many people added to the shopping cart, and how many people actually bought it, right? So I'm going to copy this, execute this in my system. And here you get a result. And it basically says that 35% of the people, when they look at a product view page, they actually go and add it to shopping cart. And about 23% go and check out with the product itself, right? So, I mean, you think about it, 35%, is it great that actually people added to the shopping cart? It could be maybe better. Ideally, you would love to see that 50% of the people who look at a product detail page, they add it to the shopping cart. But more importantly is if you added to the shopping cart, you would want a higher conversion to go and have people check on out. So having a 23% is actually quite low, right? It's not that great, especially added it already to shopping cart, right? So what's the next thing I want to do as a business analyst, right? The next thing here is I want to go and write another SQL command and say, hey, I want to see what are the worst performing shopping items that I have on my website, right? So here I also it has a pretty wicked SQL command here. It's going to go and basically look for the poorest ratio of getting into a buy page. And the other addition here is that it is going to do a join. And the idea here is that you can do is 87 million rows with another. So a millions and millions join from that standpoint, right? And you can actually add this. I have seen other community users do 5 joins, 6 joins from that standpoint. You can just add as many as you want. So if I execute this here, so you've got is these 5 items, right? So here the item ID actually came from the original user behavior parquet, right? This name is what we're joining on, and so I basically just created a dummy one that just added an item field in front of it, and so now you can see that that there's a join between these 2 fields itself, right? And great, you can now go and see that the ratio here for this top item, not even 1%. It's like 3% of 1% actually bother to add this item into the shopping cart. And so you, as a business analyst or a merchandiser, you can imagine, why would only less than 1% add to a shopping cart? Well, it could be several reasons. It could be the product page is horrible, right? The product description was absolutely horrible. The pictures are bad on that page. The item that I was searching for and looking for, this isn't what I was looking for, right? So you can imagine that this item, that the time that someone put in this item, you're not even getting a fraction. You're getting a small fraction of 1% that's even bothering to even add it to the shopping cart. So it's a big issue, right? Actually, let's run this again, right? Just to go see, you'll see it's going to same results. But what I wanted to show you here is the drop in time, right? So here before we were about 4.3 seconds. Because the cache, now there's the caching enable. I ran it a second time. Now you can see the time actually dropped to about 3.9, right? And I could probably even make this faster if I build a materialized view behind this and whatnot. But I just wanted to show you just raw out of the box across 87 million records, you're already getting this type of performance, right? Okay. So let's double tap into that item. That item is pretty horrible. So what you want to do is you want to figure out like what did actually people do on that item itself. Yet again, I have a pretty sophisticated SQL statement here, and I'm going to execute this. And so what this tells me is that of the 2,700 users that came onto the website or onto this product page, a lot of them just looked at the product view page and then just bounced. That's it. They left. 43 people clicked refresh once. 4 people clicked refresh twice. A little bit interesting. Only 2 people. Only 1 person from that standpoint actually looked at the product page and then went to a cart. And another person actually did another interesting journey. They actually saw the product page, went to the shopping cart, and went back to the product view page. So that's a really interesting journey itself. But you can imagine here is that, look, if you're going to go and enhance the conversion rate, they should be product view page and they should go to a shopping cart and they should get to buy. So nobody went even to the buy page from that standpoint. Somehow this one person out of like maybe, 2,800 visitors somehow didn't even get cross the line to get to a buy page. So there's a lot of things to work on this product and in terms of the whole checkout process itself. All right. So this is, yet again, this is just a sample scenario of 3 common scenarios that a web analyst would go do. So this is a great way for how you can go and use StarRocks against Apache Hudi data. Bonus is what if I wanted to go and figure out what's happening on the back end. So you can actually do explain analyze, and you write that in front of the select statement. And what you'll do by doing that, it will actually then tell you how this select statement ran. So where it spent most of the time here, you can kind of see it went to what we call as a Hudi scan, right? But if you double tap into the Hudi scan itself, it actually did not look at every single record. It actually went to where is that? I want to get to that part that says, yeah. So here you can actually see is that it actually sub-selected a much smaller portion. So basically what happened was that even when we executed the command, the cost-based analyzer said like, okay, let's rewrite this query to a much more faster execution. Let's scope down the amount of data that actually applies to us and then scan that subset. So of that, that's why it came out to a much smaller set. So it's like the 3K amount of records. That's why you got the 2,800 plus in there as the final result, right? So anyways, you can dig down into this. We also have within the GitHub article, you can also see how the way that we do the aggregation, when we do the sorts, when we do the joins, what type of joins. So here we did a hash join from that standpoint. You know, all these various things, we give you all the details underneath. All right. So with that said, let's turn it back to Nadine.
Yeah, I think we're getting close to time, so we're happy. If you guys have questions, if you want to post them on the LinkedIn chat, I can go ahead and answer. I didn't see any questions so far, so I'll give you guys a few minutes if you have any questions about Hudi and StarRocks and stuff. So I'll kind of give it a few minutes. But Albert, I have a question. One of the questions I had is what kind of like SQL functions are supported on StarRocks? You showed a little bit with the query, with like the complex analytical query you had.
Yeah. So since we emulate the MySQL, we actually have re-implemented a lot of the MySQL functions in there. But as you can imagine, MySQL was designed for OLTP. So it doesn't do a lot of analytical functions like the aggregations that I mentioned, right? We also have implemented time series type of functions that you typically don't see inside of MySQL itself, right? So in that sense, we are a hybrid. Our idea here is like we're going to take the best of the MySQL functions and then augment that with what we see as analytical use cases to extend the functionality, right? So I would also say that I think we do a pretty good job, but we're always building more and more functions, and so feel free to check it on out.
Cool. All right. Do we have any other questions? I didn't see any, but if you guys want to post your questions on the LinkedIn chat, I'll follow up in a couple hours. There's sometimes a delay on the questions. But I think that's it. We have upcoming LinkedIn live sessions next week with the Hudi Community Sync featuring Daniel Ford. So I'll share the link to that. And if you have any questions, you can find us on Hudi Docs, the Slack community. Please like and follow us on LinkedIn. If you like and use Hudi, please give us a star on GitHub. And I'm sure the same thing for StarRocks as well.
Thank you for having me, Nadine.
Cool. All right. Thanks, guys. We'll see you next week.
Bye.
Bye-bye.